this set operations. This actually is the continuation of my first tutorial video that I posted a week ago that is about set theory. I suggest that you watch it first because we're going to use that concept in this full tutorial. So let's start. Okay, so set operations. We actually have many set operations, but we're going to tackle some of them. The first one is the union, and then we have the intersection, difference, and power set. And by the way, I'm going to collaborate the Venn diagram and set operation with this topic because somehow Venn diagram will help us to understand better the topic about the set operation. So, what is Venn diagram? Venn diagram is a graphical representation of relationship between set and its operation. So later you will see how we are going to use the Venn diagram for us to understand better the set operation. So to understand it better, I'm going to give you this example. For example, we have the set A and then we have the set B. Set A has an element of 1, 3, 5, 7, while the set B has an element of 1, 2, 4, 6. So, to do the Venn diagram, we're going first to draw the set A inside the circle. Alright, so we have here the circle, and we write the 1, 3, 5, 7, which is the elements of set A. It's easy as that. We're going to do it on the set B. So as you can see here, set B has an element of 1, 2, 4, and 6. So the next step is this. We're going to unite this set A and set B. As you will notice, the element that is number 1 is inside the set A and set B. That is actually one of the operations in this set operation. So later we'll discuss it, don't worry. So I'm just giving you the little concept how to do the Venn diagram. So hold on with this Venn diagram because we're going to use this one for the rest of our slides. So let's start with the set operation. The first thing about set operation is the union. The union denoted by U. Anyway, this symbol is used to this symbol is used to show that a two set is united. So again, union is the union of a collection of a sets in the set of all distinct elements in the collection. When we say distinct elements, as from the definition of a set, it should not be repeated. I mean the elements inside the set should not be repeated, and it is one of the fundamental operations through which sets can be combined and related to each other. So originally, okay, we have again this set A has an element of 1, 3, 5, 7, and set B has an element of 1, 2, 4, 6. Then A united or union with B is equal to 1, 2, 3, 4, 5, 6, 7. So we just write all the elements of B and write all the elements of A. As you will notice, they do have the number 1, and the number 1 is not repeated inside the set because as from definition, set is a collection of a object without repetition that is understood. Okay, we have this diagram. If we will do it on a Venn diagram, it will be like this. So we're going to shade all of the elements, which is 1, 3, 5, 7, and 2, 4, 6. Just simple as that. So that is the union. The next one is that the intersection. Intersection. The intersection of A intersects B of two sets A and B is the set that contains all elements of A that also belong to B, or equivalently, all elements of B that also belong to A but no other elements. And again, we're going to use this symbol to connote the intersection. Alright, so the intersection of set A and B is 1. Okay, as simple as this one, we have this Venn diagram. Set A has a 1, 3, 5, 7, and set B has a 2, 4, 6, 1. We're just going to pick the elements that is present both in set A and set B. And in our example, we have the element 1. So what if on set B we're going to put this a number 3? That is possible. The number 3 should be here if set B has a number 3. Since we do not have, we're not going to write it. So simple as that. We're just going to write the elements that intersects the set A and set B. Okay, next one is the complement. A complement of a set A refers to things not in, that is, things outside of A, not in A. The relative complement of A with respect to set B is the set of elements in B but not in A. When all sets under consideration are considered to be subset of a given set universe, anyway, this symbol means universe. It means all the elements are included inside and outside of the sets. The absolute complement of A is the set of all elements in universe but not in A. So for us to understand it better, we're just going to do this again. We're just going, of course, to use the Venn diagram. The complement of A, which has an element of 1, 3, 5, 7, is 2, 4, 6. So how are we going to understand it? The complement of A, it means this is the letter A. Complement of A is 2, 4, 6. It means that we're not going to write anymore the elements inside the set A. We're just going to pick anything or any elements outside the A. That is because we use the term complement. And the same with the complement B. The complement of B, which has an element of 1, 2, 4, 6, is 3, 5, 7, which means we're not going to pick this one. We're just going to answer this as the 3, 5, 7. So how are we going to do it? So this is the complement of A, which is the 2, 4, 6, and then the complement of B, which is the 3, 5, 7. So still, we're not going to use the number 1 because number 1 is inside the complement B and inside the complement A. So as easy as that, we're just going to pick outside the elements of a given set. Okay, next, difference. Difference is somewhat similar to complement. If A and B are sets, then the relative complement of A in B, also termed the set theoretic difference of B and A, is the set of elements in B but not in A. We still have this kind of example. A has an element of 1, 3, 5, 7, and B has an element of 1, 2, 4, 6. A minus B is equal or has an element of 3, 5, 7, and if we're going to differentiate it, we're going to use the Venn diagram for us to understand it better. So we have here 1, 3, 5, 7, and 2, 4, 6. So this is originally our Venn diagram. So if we're going to deduct the B in A, of course, we're not going to use the A, or rather, we're not going to choose inside or any elements inside the set B. So in this case, if we're going to deduct A to B, the remaining will be 3, 5, 7. That thing will be the same with B minus A, or B difference of A, and the answer will be 2, 4, 6 because we are going to deduct the A, or not going to include the whole A in B. That's why anything that is inside the B but not in A is selected in our answer, which is, in our case, our answer will be 2, 4, 6. Then the next one is a symmetric difference. Symmetric difference is somewhat similar with the XOR. So if we have here an example as set A has an elements of 1, 3, 5, 7 and set B has an element of 1, 2, 4, 6, what will be our symmetric difference? As easy as this. So originally this is our Venn diagram. So we're going to write all the elements except to the elements that has been intersected by the sets. In this case, number 1 is not included because number 1 is the element that intersects the set A and set B. So the answer will be 3, 5, 7, 2, 4, 6. As easy as that. So another thing about the set operations that we also have the power set. Power set do not have actually a Venn diagram. It just shows all the positive combination. So if our example will be A has an element of X, Y, Z, we're going to write all the positive combination. So the first thing is nothing. So this is 0. Or we will begin with this, with always. Okay, so a single X, a single Y, a single Z, and then X and Y, X and Y. And the next thing is that we have the X and Z. Alright, so the next thing is that we have the Y and Z. Okay, so the last thing is that we have the X, Y, and Z, which complete our combinations on this set. So again, set A that has an element of X, Y, Z has a power set of 0, X, Y, Z, X, Y, X, Z, Y, Z, and X, Y, Z. So that is as simple as that. So I hope you learned something from these operations. If you have comments, just leave your comment. If you like it, just simply like it. I hope you learned something from this. Thank you. And this is from Lynn Velasco. Thank you for listening.